So a lot of research has been done, starting from data collection to study different types of biomarkers, to the development of prognostic prediction models, with having in mind that they are supposed to be used in the clinical practice to support clinical decision. So my work focuses on the prognostic prediction models, and as I told, the main idea is to deploy a decision support system where, given a new patient, I can give a likely prognostic based on the past history of patients with known diagnosis. And actually, many prognostic models have been proposed. Still, they are hard to apply in the clinical practice. Why is that? So one of the reasons is because the lack of a useful measure of uncertainty on each individual prediction. Because when you evaluate those models, we'll evaluate them on an individual test set or validation set, but we are evaluating the general error rate, like with measures like accuracy, for instance. But it doesn't say us anything about the uncertainty of an individual prediction, and that is paramount for the clinicians. They need to know how much they can trust on that prediction to pursue with the treatments based on that. Moreover, we also think that's useful to give time of conversion, so the clinicians can timely adjust the treatments. And we test already the prognostic prediction to Alzheimer's disease within time windows, and we proved that we could achieve better results. So this is the proposed approach of this work. It's a stepwise learning approach, when in the first model, model 1, we will try to predict which patient will convert to dementia or remain stable. And we just assign those classes, like this converter or stable MCA, if the confidence level is above a certain threshold. If not, we say that we are not sure to give that class. And then those patients that are classified as converters, we'll try to we will feed them to model 2 and try to classify them as a short-term converter or a long-term converter. Once again, we just attribute the class if the confidence is above a certain level. In this case, we consider short-term if the conversion happens within the 2 years after the baseline, and the long-term converters if it converts between 2 and 4 years after the baseline. So to test this approach, we use data from ADNI. We consider a follow-up of 4 years, and we use essentially neuropsychological tests. These are the data. I can use maybe the mouse. These are the data for model 1, so I have to distinguish between the two classes, stable or converter MCA, and then those that convert, we differentiate between the late converters or the short term. As you can see here, we have an imbalanced data set. In order to assign some confidence levels to each prediction, we used Conformal Prediction. That is a framework that is based just on one assumption, that examples are independently and identically summed for the same distribution, and it can be applied to any classification algorithm. So just for you to have a general idea of how it works, imagine that we have a training set described by a vector of attributes, and we have two classes, 0 or 1. Then, given a new example, we want to predict the class. So we will assign each one of possible classes to this new example, and then we will see how non-conform or dissimilar this new example is with the training set, considering each one of the classes. In order to do that, we have to find a non-conformity measure to compute the non-conformity with the training set, and then use this to compute the p-value that is used to assign the class. Basically, the p-value counts how many examples are more different from this training set than mine. So once we have the p-values, we can use conformal prediction in two setups, using prediction regions or forced predictions. In the prediction regions, for a given confidence level, the conformal predictors always output a prediction region that contains all the classes that has a p-value above higher than the significance level. So we can have just a single prediction for class 0 or 1, or it can also happen that we have both classes predicted or any. If we used forced predictions, we always have just one prediction that is the one that has the largest p-value. And we have also the confidence and the credibility to show us how certain our classifier was. This is just an idea of the workflow. We start by splitting the data in 80% to training, 20% to test the stepwise learning approach. So we have to train 2 models, that was model 1 and model 2. We deal with feature selection and class imbalance. And then once we have the trained models, we use the test set. We run the model 1, and we do prognostic predictions to classify in stable or converter MCA. Then those that were classified as converters will be fed to model 2, as I explained previously. So here are the results when we are training model 1 and model 2. We can see that for model 1, the prognostic prediction, we achieve good results. Still for model 2, the results are not so good. And we know that the classification task is more challenging in model 2 because we are distinguishing between types of converters, and in model 1, we are distinguishing between a converter and a stable MCA patient. Still, we don't know if these not so good results are due to this challenging classification task or to the class imbalance that was present on the dataset. Here we present the results when we apply the stepwise learning approach. Basically, we show how many cases were correctly identified at each step of the approach. In the left, we have the test set, and we can see that about when we apply model 1, about 84% of non-converting cases are correctly classified. Then, regarding the converting cases, we have 79 to 83% of converting correctly classified, but only 60% are the late-term converters. So once again, it can be due to the class imbalance. For those patients that converted, we run model 2, and we could see that about 64% of the short-term converters were correctly classified, but the long-term converters, in fact, the results were poor. So here we have the patients that has no class assigned because the classifier was not confident enough. We can see that when we ask the classifier to be more confident, this percentage is higher, as expected. And these are the results using the forced prediction approach. I didn't show those using the prediction regions approach because they were quite similar. The main difference was that the percentage of non-classifiable cases was higher. So it can maybe, with the prediction region approach, it seems to be more stringent with the trustiness required to make a confident prediction. So we also briefly analyzed the set of features that were selected for each one of the models, and we could see that to model 1, to do the prognostic prediction, it selects a lot of memory subscores and the ADSCOC total subscore. And in model 2, to predict most likely windows of conversion, a lot, besides some memory scores, also a lot of neuropsychiatric measures were selected, like patient's appetite, depression. So it can tell us that although we have some common tests that are predictive for both problems, some of them are different. These are different classification tasks. Just to summarize, we propose a 2-step supervised learning approach, where at the first step we classify patients as being stable or converter MCI, and then we predict most likely windows of conversion. We complement these predictions with some confidence levels, which is really important for the clinicians, even for those patients that were not confident, where the classifier was not confident enough. It's important because they can prescribe more specific exams. The exploratory results are promising, but compromised by the small number of examples for the long-term conversion. And as I told, the prediction region approach seems to be more stringent on the demanded trustiness to make a prediction. So as future work, we'd like to validate our approach with the larger data sets and also try some different confidence levels and cutoffs of the time windows, and to further evaluate the neuropsychological test that was selected. And finally, the main goal is to deploy a model to be used in clinical practice and support clinical decision. So here are the references. Thank you.